Today we're going to be talking about the fundamental theorem of calculus. In the last video, we talked about evaluating definite integrals by calculating the area under the curve in the region that we were interested in. Now, all the examples that we did in that video were calculating the area when the function made a really nice shape with the axis. So for instance, a triangle or a rectangle. But most functions aren't going to make such an elegant shape that we automatically know how to calculate the area of using geometry. So how do we calculate those definite integrals? That's what we're going to talk about today. Let's start with the first part of the fundamental theorem of calculus. We're going to be thinking about little f, and let little f be continuous on the interval in question. Let's define capital F to be the integral of little f. Then the derivative of capital F will just be little f. That was a lot of words to say something that looks pretty intuitive. Basically, if we have a function that's defined to be the integral, then the derivative of that function should cancel out with the integral. In particular, though, what you should notice here is that I've got an x as one of my bounds. What this means is this bound is fluid. It's going to be able to be a placeholder for any value that we want. And that's going to be different from the variable in question, which we're saying here is t. The reason why these are different is just to be able to plug in x as a bound. If this were f of x dx, then we wouldn't be able to have x as both a variable and a placeholder for a constant. Okay, so again, with our bound, we're having this upper bound be a variable that we could plug any constant in that we want. So let's see what this looks like in an example. Let's say we define a function to be the integral from 3 to x of t squared minus 17 dt. Then if I took the derivative of this function, this effectively cancels out the integral and I'm left with x squared minus 17 is my derivative. This 3 here doesn't really matter, right? This can be any constant down here. The important thing is that I have the x on the top. The reason why this can be any constant, we'll see a little bit later, but when I'm taking the derivative, I'm bringing myself down a dimension. So what's happening down here with this constant doesn't really matter. Now this x is a placeholder, which means I can put any number that I want there. So for instance, if I wanted to know what the integral from 3 to 5 of my t squared minus 17 is, then how would I know? Well, this would just be whatever this capital F function is. If I plugged 5 into it, I would get this integral, right? So I maybe don't know what the capital F is right now, but what I do know is if I wanted this definite integral where I had a number up here, I could just plug that number into my capital F function and still get the value of the integral. So let's try this with some variables, and you'll see why this is helpful in a second. So I want to find this sort of general integral from a to b. And I've defined this function capital F to go from c to x, where c is just some random constant. Okay, now the problem with calculating this integral as is this capital F has a c on the bottom here, but there's no c in our bounds here. So what do we want to do? Well, we can use one of our properties of definite integrals that we talked about before to basically break this integral into two pieces. So we're going to let the first piece go from a to c, and then we're going to let the second piece go from c to b. Okay. Why did we do that? Well, now we've broken this up into pieces so that c now does exist in our integral, so we can use this definition that we've made up here. Now, of course, the definition has c on the bottom, and in this first one we have c on the top, but that's okay. We know we can switch our bounds by multiplying by a negative sign. F of t dt plus the integral from c to b f of t dt. Okay. And now this looks exactly like our definition for capital F, right? So if I'm going from c to a, that would be capital F of a. And if I'm going from c to b, that would be capital F of b. So what does this mean? This means that any definite integral that I have, instead of calculating the area, if I know what this capital F function is, then I can instead just plug in the endpoints and subtract. That's pretty easy. And it's even better if we're looking at a function that we wouldn't even be able to solve by just calculating the area of the shape that it makes. So our goal is to find what that capital F is, and then we can plug those endpoints in. Well, the good news is we know what this is. This is our fundamental theorem of calculus part 2. So what the fundamental theorem of calculus part 2 says is actually that capital F can be any antiderivative that we want of little f. So if we're trying to find the area under the curve of a curve that doesn't make nice shapes, that's okay. We can just take an antiderivative like we did when doing indefinite integrals, and then plug in our endpoints and subtract them from each other. So let's see an example. So I want to find this integral. So the first thing I'm going to do is I'm going to find an antiderivative of x squared minus 17. So again, we're just looking for any function where if I took the derivative of it, I would get x squared minus 17. So for example, I could do 1/3 x cubed minus 17x. And let's think to ourselves, double check power rule. If we bring this 3 out front, that cancels with the 1/3, and that leaves us with just x squared minus 17. That's what we wanted. Okay, great. So this antiderivative works. And the notation that we typically use here is a straight vertical line with our bounds on the sides. That just helps us remember what our bounds are. Okay, so now what does our fundamental theorem of calculus say? It says I just plug in my bounds into my antiderivative and subtract them. So this will give me 1/3 times 2 cubed minus 17 times 2. And then I subtract off the lower bound. So 1/3 0 cubed minus 17 times 0. So this whole thing is going to equal to 8/3 minus 34, whatever that is. But this was so much easier, right, than if we wanted to make our graph, this is not to scale, and we wanted to know like what is the area of this piece right here. How in the world were we going to figure this out? I don't know. But finding our antiderivative and plugging in, that was quite easy. Now notice that we can use any antiderivative that we want. Why is it? Why isn't there a specific antiderivative? Well, let's think about what all the antiderivatives would look like. So if we actually did our indefinite integral, right, we should have 1/3 x cubed minus 17x, and then we should also have a plus c here. Why were we allowed to not have that plus c? We had really emphasized when we were doing indefinite integrals that that plus c was really important. Why did we leave it out? Well, let's imagine that we did have our plus c here, and again, we're going to evaluate from 0 to 2. Then this would equal to, again, 1/3 times 2 cubed minus 17 times 2 plus c, and there's no x there, so the plus c just stays exactly the same, right? The 2 doesn't impact it. And then again, we're going to subtract off our 1/3 times 0 squared minus 17 times 0. And again, when we have our plus c, there's no x there, so it just stays as plus c. And you'll notice that I've got a plus c here, and when I distribute the minus sign, a minus c here, so they cancel out, and I'm left with exactly the same thing. So it does not matter which antiderivative you use, because your constants will end up canceling when you plug in your bounds. Typically what this means is people just don't add a constant at all. We're going to imagine our constant is 0. But if you really want to have a constant in there, you absolutely can. So this is our fundamental theorem of calculus. If we want to find a definite integral, we just find any antiderivative we want, plug in the bounds, and subtract. So we can use this for a variety of applications, which you will learn more as you go through the calculus sequence, but let's just look at a pretty basic one right now. This is the mean value theorem of integration. And it's basically the integral form of the mean value theorem that we talked about a few weeks ago. So what is this saying? This is saying that there's going to be some value c where my integral is just going to be f of c times b minus a. What does this mean geometrically? It means that if I have some function, then, and I want to know the area under the curve of this function, let's say this is a to b, then there's somewhere in between that interval where if I make a rectangle of that height, then that rectangle will have the same area as the blue under the curve. That's obviously not to scale, but there's somewhere along here where the area of that rectangle, the orange, is going to equal the area under the curve, the blue. So let's take a look at an example. So we want to find that spot in our curve that the rectangle, the area of the rectangle is going to equal the area under the curve. So we're going to do this very similar to how we did the mean value theorem before, right? So what we're trying to do is we're trying to find this C. So let's start by finding what that thing should equal. That's like when we were finding the f of b minus f of a over b minus a from the original mean value theorem. All right, so we'll start by finding the integral. So the integral here is 1/4 x to the 4th. That's our antiderivative, and we're evaluating that from 1 to 2. So we go ahead and we plug in. So this is 1/4 times 2 to the 4th, which is 16, minus 1/4. That's when we plug the 1 in. So this gives us 15/4. So 15/4 is the area under the curve. That's the area that we're looking for. So what we're asking is, what is the height of our rectangle, or where, if we map up to the height of our rectangle that has the same width as my graph and also the same area, right? Okay. So what is f of c? Well, f is x cubed, so c is going to be c cubed. 2 minus 1 is 1, equals 15/4. So the c that I'm trying to find is the cube root of 15/4. Okay, what does this mean geometrically? Let's actually try to visualize this. It means here's the graph of the cube root, and let's say here's 1 and here's 2. So we're trying to find this area. Actually, we already know this area. This area is 15/4. We're trying to find where along the curve, if I make a rectangle, will it have the same area? And that's going to be about here. So the area of this rectangle is going to be also 15/4. This is not that surprising, because if you look at the area of this little bit that is not included in the blue, it looks about the same as the area of this bit of blue that's not included in the rectangle. All right, so what have we done here? We found a spot where I can find the area of my curve as a rectangle instead of as a funky shape. We like to think of that as the average value of our function, right? Because the area of our function in that spot, if we just leveled it out at that specific spot, then I would have the exact same area. So that's the average of the values of my function within that interval. And so that's what we're going to define as the average. The average is going to be that f of c. And here, what have we done? We've just divided by b minus a. So from the mean value theorem, this is the f of c that we were talking about. This is the average value of f on our interval. So we'll just take that integral, that's the area, and we'll divide by the width of the rectangle to find the height of that rectangle. Okay, so to recap, we've talked about the fundamental theorem of calculus today. Specifically, the fundamental theorem of calculus is telling us that we can evaluate definite integrals by finding any antiderivative we want, plugging in the endpoints, and subtracting. And one application of this is the mean value theorem, which says that if I'm looking at the area under my curve, there's some point in there where I can make a rectangle that has that exact same area. And that point is going to give us the average value of our function.